Okay, on to section 8.2, the nature of covalent bonding. So, in covalent bonding, atoms also are trying to obey the octet rule. So we share electrons, and it occurs so that atoms still obtain the same electron configuration as a noble gas, same as in ionic bonding. So here's an example. A single hydrogen atom has one electron, and a pair, if I have a pair of hydrogen atoms, two of them, they'll share electrons to form a covalent bond. So that forms that diatomic hydrogen molecule. So by each hydrogen sharing one electron, I wind up with a configuration of helium with the noble gas with two electrons. Various combinations of nonmetals and metalloids in groups 4A, 5A, 6A, and 7A, remember that's 14 through 17, are like the ones most likely to form covalent bonds. And they combine in such a way so that everybody gets that octet of electrons, and they're sharing various electrons. When we're talking about hydrogen, again, if I have two hydrogen atoms, each with one valence electron coming together, now they're sharing this pair of valence electrons, and that they're held together then by the shared electrons being attracted to the nucleus. And these two atoms are joined by what we call a single covalent bond. So a pair of electrons is a single bond. So again, hydrogen gas is diatomic, meaning we have two atoms of hydrogen forming a molecule. So we have two individual atoms, each now sharing that pair of electrons to make the molecule. This is what we call an electron dot structure. It's also called a Lewis structure, named for Gilbert Lewis, who invented them. And it represents the pair of electrons either by two dots, as shown there, or more often you will see it represented as a dash, and the dash represents a pair of shared electrons. And when drawn this way, with dashes, it is called a structural formula. So this is a structural formula for hydrogen molecule. The halogens also form single covalent bonds in forming diatomic molecules. So here is an example of fluorine. So this is the orbital notation for fluorine, showing the electrons in the 1s, the 2s, and that 5 electrons in the 2p. So if I bring in a second fluorine atom, also with the same configuration, we share this pair of electrons in that last 2p orbital. And so by each having one electron in the 2p and now overlapping those orbitals so that they share, both fluorine atoms achieve that electron configuration. So here's another way to describe that with the dot structure, showing that each fluorine atom contributes one electron, and they share one pair of electrons in between them, only one pair. We also see that in fluorine there are several valence electrons that are not shared, and when atoms are not shared, that's called an unshared pair or a lone pair. So in fluorine molecule, we see that each fluorine atom has 1, 2, 3 unshared pairs of electrons. Water is another example of a covalent molecule that has single covalent bonds, bringing in two hydrogen atoms and an oxygen atom. So each hydrogen and oxygen each shares one pair, so that makes two single covalent bonds. Another example is methane, where we use carbon with 4 valence electrons, so it needs 4 more to achieve that octet, and so we bring in 4 hydrogen atoms, each one sharing a pair of electrons with carbon, making a carbon in the center with 4 hydrogens around it. Not only can atoms form single covalent bonds, some atoms can come together to make double or triple covalent bonds by sharing 2 or 3 pairs of electrons between atoms. Here's an example of a carbon dioxide molecule, CO2, that contains 2 double bonds. So 1 carbon atom with 4 valence electrons and oxygens each with 6, or wanting 2 more. And so we wind up with 2 shared pairs between each of the carbons and oxygens, and we have 2 double bonds. Atoms such as carbon, oxygen, nitrogen, and sulfur commonly form double bonds. Triple bonds can be formed between carbon atoms and nitrogen atoms. Those are the ones that commonly make triple bonds. And so N2, the nitrogen molecule, contains triple bonds. Each nitrogen has 5 valence electrons, and they each want 3 more. So they make 3 bonds in between them. That's a triple bond. Next, we'll talk about a coordinate covalent bond and how it's a little bit different from a regular covalent bond. The example we're going to look at is carbon monoxide, just 1 carbon and 1 oxygen, has a little different kind of covalent bonding that we saw in the other examples. In this situation, carbon needs to gain 4 electrons and oxygen only needs to gain 2 electrons. So we're not even up there, and we only have one oxygen, so we've got to do something a little different. If we begin with a double bond between the carbon and oxygen, that makes the oxygen satisfied with 8 covalent electrons, but carbon is not. So what happens is oxygen donates one of its unshared pairs, and so one atom contributes both of the electrons in the bond, and that's what's called a coordinate covalent bond. So instead of carbon contributing 3 and oxygen contributing 3, carbon only contributed 2 of the electrons in this group, whereas oxygen contributed the rest. So in a coordinate covalent bond, one of the pairs comes from a single atom rather than shared. Additionally, we have polyatomic ions, which are a group of atoms that are held together by covalent bonds and also coordinate covalent bonds. But at the end of this bonding, we wind up with a charge on the group of atoms, making it an ion. So the ammonium ion is an example of a polyatomic ion, and we have an ammonia molecule, NH3, which has 1 unshared pair of electrons on the nitrogen, and then a hydrogen ion that lost its electron, so really essentially it's just a proton, and when those two bond together, the nitrogen donates its unshared pair to bond with that hydrogen ion, and making that a coordinate covalent bond. And then the whole thing, you see here, gets this bracket, and this bracket shows that everything has a charge, and this whole ion, this is called the ammonium ion, NH4, with a positive charge. Polyatomic ions, some are positive cations, most of them, however, are negative anions. They contain both covalent bonds and coordinate covalent bonds, and any compound that would contain a polyatomic ion would have both ionic and covalent bonding at the same time. The last thing to talk about in this part of the section is bond dissociation energy, and which is a way that we measure the strength of a covalent bond. When individual hydrogen atoms combine to form a hydrogen molecule, that H2 molecule, a large amount of heat is released. And releasing heat means energy is giving off, suggests that the product is more stable than the reactants. In fact, the covalent bond in an H2 molecule is so strong it would take 435 kilojoules of energy to break apart all the bonds in a mole of hydrogen. This amount of energy is called the bond dissociation energy, and that is the energy required to break the bond between two covalently bonded atoms. So that measures then how strong the bond is. So to compare, carbon-carbon bond has a dissociation energy of 347 kilojoules per mole, which is still very high because they're very strong bonds, and they're very unreactive because the dissociation energy is so high. So a high dissociation energy or a large dissociation energy corresponds to a strong covalent bond.